and we call it Jarvis. I'll come to the part why I name it Jarvis. And this whole project is actually a part of something called Materials Genome Initiative. It is a project initiated by ex-President Barack Obama in 2011. The idea was to make a discovery of a material. It takes around 10, 20 years from the lab to actual implementation in industries. So can we expedite the process using computation, experiment, and artificial intelligence or data analytics? So I'll touch base on that too. And I'd also like to thank Brian DeCoste and Francesca Tavazza at NEST who helped me in this project. There's a bunch of people involved in this project from different national labs, such as Lawrence Berkeley National Lab, and different universities such as Stanford and Penn State and stuff like that. So I'd like to acknowledge them too. A brief outline of the topic. So I am pretty sure I'm talking to a very general crowd here on data analytics. So how many of people here know about band gap? Raise your hand. Just maybe 3, 4. Yeah, okay. So I'll explain a little bit like properties of materials and what are the different techniques in AI that we can use that. And feel free to stop me and ask me questions and clarifying questions if you do not get me what is a band gap or magnetic moment and stuff like that. Please feel free to stop me. So I'll talk about different component of Jarvis, Jarvis FF, which is a classical mechanics part, Jarvis force field, we call it, Jarvis density functional theory, which is a derivation from quantum mechanics, and JARVIS-ML, which is part of Jarvis machine learning. And then I'll talk about how do we represent a material to a computer. There's a huge, like 200 years of physics research, right? Maybe more than that. And how do we take that knowledge and put into current status of AI? How do we visualize multidimensional data in materials? And I'll focus on a specific algorithm in machine learning called gradient boosting decision trees. I am pretty sure we heard a lot of talk about neural networks, so I'll try to recast my talk along that gradient boosting decision trees. And lastly, I'll talk about how to apply this machine learning model to screen materials or select materials. So back in the days of Edison used to combine different materials in lab and come up with a super fantastic material. That's like age history. So now what we do, instead of doing that trial and error process, which is called Edisonian approach, we use AI or machine learning to fasten or accelerate the process. And we'll talk about a web app and the data tools that we have generated so that in public our scientists or researchers can use that facility as well. So the current status of AI or artificial intelligence in materials. So for any successful AI application, what we need is really high fidelity data. This is really a bottleneck. I just want to emphasize that if you want, to do an AI on cat and dog images, you want to take all the Facebook images or Picasa images and to characterize whether it's a cat or a dog images. It's pretty simple because you really upload all your data on Facebook. So they have all the data there. But for machine learning, for material, it's not that trivial. For materials, you really have to generate data using either classical physics, quantum physics, or several experiments. And that is one of the bottleneck for applying AI in materials. So AI in materials is not really a new topic. It's been there for 20 years, but it's really taking a jump in present decade because of this really rise in computational resources we have. And then we talk about algorithms. So there are different algorithms which are fortunately available in like scikit-learn and TensorFlow, LightGPT and stuff like that. And then you need a validation strategy. It's very easy to say whether an image is predicted from the AI is a cat or dog or not by visual eye. But how can we do that? How can you validate your model from materials? That's the important question. So I'm going to talk about that too. So as I mentioned, because of recent rise in computational resources, there are different databases coming up for materials. And they hold their origin in something called International Crystallographic Structure Database. So this is a database coming from directly from NIST and in Germany, and they have put together different materials database. So what they do is they take X-ray diffraction, something sort of a signature of material, and make at least like 100 or 1,000 of material database, and people can easily access it. So we use that database and uses classical as well as quantum mechanics to generate data. So you have the materials, you have the data, and now we also use this gradient boosting decision tree to find the patterns in them. So we have to note that the grand unified theory is not solved yet. So there's no actual universal equation yet, that at least I know. So even if you don't know that, what we can do is whatever we have, we find the pattern in that data. And doing that way is I think is the next step, next boost in AI community they're going to have. So instead of finding a universal law, why don't you find a data analytic model which find the trend in the properties of different materials? And it's not a science fiction. It's not in the science fiction anymore. It's really implemented in like aircraft industries, like how to make lightweight and strong alloy for your aircraft, medicine design, and medical diagnosis. I'm going to focus mainly on the material side. So what's the motivation of this talk? So the motivation of this talk is really to bridge the gap between sophisticated materials community or physics community and the data community. They really talk in a different language. So we want to bridge the gap between them by providing the tools publicly so that they can use for their own algorithm, their own infrastructure. And if you just look around here, you are really wearing, this is also a material. You have the phone you're holding is made of different types of material. The thing we eat, the thing we travel, you're surrounded by a variety of materials. And in a recent Nature Chemistry paper, they projected the total number of materials in the world, at least on the Earth. I'm not counting over the space and galaxy and stuff. Just on Earth, they counted that total number of materials can be up to 10 to the power 100. So it will take about 100 generations if you really do the traditional way of experiment and theory. And so why don't we just expedite or accelerate the process using machine learning? So the idea really came from, I was literally watching this movie, Jarvis, from Iron Man. How many are familiar with the movie Iron Man here? Pretty, that's good. So it's one of my favorite movies. So I was watching this, and I saw this really fantastic idea of Iron Man saying, oh, Jarvis, make me this titanium gold alloy so that I can travel in space. Fine. But if you see it from a physicist's view, what he's saying is, find all the materials available and predict me all the a material which is suitable for a particular application, spacecraft, or something like that. And then you fabricate it. So it's an automated process if you break it down. A simple part of movie can lead to a whole project. You can see that here. So, so in the movie, I think the full name of Jarvis is just a rather very intelligent system, something like that. So I give a fancy name because I don't want to be in like clash of names and stuff like that. So I gave it joint automated repository of various integrated simulations. So really the idea is to automate theory and experiment and to build new and discover new materials. And as a physicist, I'm also interested in finding interactions in the materials. So the materials you are sitting on, you are looking into, are made of tiny atoms. So what I'm seeing in the middle is like, in the next, is like tiny atoms in silicon. And what I see is that they interact. Or in other words, they talk to each other, which we don't know. And this talking, how we explain this is physics. And it's a very layman explanation, but this is actually sort of how it works. So for that reason, there are different laws, like Coulomb's law. Coulomb's law tells you have the charge and how they interact, right? Q1, Q2 over R, and I guess school level physics. So this thing works if you have very ideal model. For neural materials, it's not that simple. So for that, I'm going to talk about 3 different components: force field, density functional theory, and machine learning part. How do we understand this language of materials? And once we understand the language of the materials, then only we can say, okay, I want this material, you have to become this. So this is the control part where we envision it will come from. So as I said, there are 3 components in Jarvis-FF, DFT, and machine learning. So we know this example of apple falling on someone's head. and that led to a new area of science, Newton's laws. So how do you actually apply for materials? We have heard in 8th grade or school physics. So we know that materials are really made of tiny atoms, and that atoms can be governed by several laws, such as Coulomb's law, but they are, after Coulomb, there are several other formalism has come up, which I'm saying this is really a specialized science level question like EAM, EIM, MEAM. These are different formalism which come after Coulomb to understand how materials interact classically. And for that, we have made a database. For example, if you want to see how does aluminum and oxygen interact, you can go to the force field component and see what are the all possible materials and what are their properties, such as their hardness, their bulk modulus, how strong or stiff they are, their energetics. So I was just explaining a few minutes ago, what is energetics or formation energy. So I was explaining that you have a couple, you have male and female living together or something, and if the total entropy of the system is very disordered, then it's going to be breakup, right? So it's called this. It's the same way the materials also interact, the atoms. If aluminum and carbon, if they are making peace with each other, they'll make a compound. If they are not, they're going to break up. So this is how do we explain the energetics or formation enthalpy. Similarly, I will use something in later properties called band gap and other properties, which I'll come to the next part, which is density functional theory, which is really an approximation of Schrödinger equation. So how many here are familiar with Schrödinger cat? Good, that's good. So we heard that there's a dark room and you don't know whether a cat is alive or dead, right? So if you consider a cat to be alive and dead as one and another state, so we call it a state of cat. Similarly, the electrons in a system are not that different. Electrons also can occupy a different, only fixed state in a material. That leads to a different class of materials called metal, semiconductor, and insulators. So if it's a metal, for example, it can easily correct electrons and electricity if it's like a copper wire in your home. Similarly, a wood cannot conduct electricity because it's an insulator. Similarly, a semiconductor such as silicon is really fascinating because there's a small gap between something called a valence band and conduction band. And once you pump a little bit energy, I brought this example to explain. So this is a good example of understanding semiconductor. So you have something here full of electrons, and here there's no electron. So if I in a metal, generally there's a full range. I mean, it's all connected. So water can flow from here to here. Similarly, electricity. So metal can easily, in metals, electricity can easily flow. But for semiconductor, there's a gap. So you really need to push a little bit. Oh, I'm not going to push it. So then it will push the electrons there, right? So that small voltage is what actually led to all Silicon Valley industries. That's a small history about it. So this is called band gap. The gap you see is called band gap. So I talked about formation energy, band gap. And there are different properties such as refractive index, magnetic moment, effective mass of carriers. These are all terms I've given the reference for a really nice books. You can take a look on that. So we have generated around 30,000 material property database in our Jarvis DFT. It has like, I tell you one example of silicon. There are 30,000 materials and there are several properties, around a million or a few million properties. And for that, we are using 5,000 computer cores for the last 4 years. And it's constantly day and night running to calculate these properties using approximated way of Schrödinger equation called Kohn-Sham equation. And for the Kohn-Sham equation, actually, Walter Kohn got Nobel Prize in 1998. So it's really a good history. And you can find the detail and at the website that I have just provided. By the way, the slide I'm presenting will be is already available on SlideShare. I'll give the link at the end. And there comes the machine learning part. Let me see how I'm doing with time. In the machine learning, what we really do is what I call drawing the line in a layman way. So you have the red dots on the right-hand side, red dots and the green dots. How accurately can you draw the line to separate them is sort of what you are doing in machine learning. And really, there are different algorithms which have been developed. There are supervised, unsupervised method. in machine learning. I'll be focusing mainly on supervised machine learning using gradient boosting decision trees. And I'll be predicting different properties such as band gap, formation enthalpy, using machine learning, not using experiment, not using classical physics or quantum physics, but really machine learning. So before I go into details of the machine learning part, these are really typical steps you want to do sort of checklist before you do any machine learning. So you have to have a descriptor. So for example, in a cat and dog image, it's really the pixels and the RGB colors that are the descriptor of an image. For materials, it's not that simple. And we really worked hard on this to come up with a better descriptor of material, which I'm going to talk about. And then you have visualized this. So you have, suppose you have RGB, the 3 colors, and you have 10,000 samples. So you are dealing with really huge dimensional data. So how do you visualize that? I'll do that using t-SNE plot. I'll explain that. Then after that, you do pre-processing, such as PCA and stuff like that. And then you do train test split, a very common way. And as a data scientist, what you really focus in, like hyperparameter optimization and selecting a best model. And for materials community, I would like to draw attention that what is really important is the feature importance, for example. Once you say, like, OK, I trained the model for cat and dog image, and once you give me an image, I can predict whether it's a cat or dog. That's it, end of the story. For materials community, it's not that simple. If you go to the guy who is working for physics or chemistry, have a lot of gray hairs and working for years, and you just say that, OK, this is my material, and its band gap is 6 electron volt. He's not going to be convinced. You have to really explain why it works. So you really have to be careful before we choose an algorithm in machine learning for materials. I'm going to talk about that too later. So I'll spend some time on this. So how do we represent material to computers? So as I said, in atoms are really bonded with each other. So there's something called bond length. So if this is my atom and this is my atom, they have a bond length, which I represent here with R. And that, how many are there in each bin? So I take, for example, 0 to 1 nanometer size, and from there, how many in each bin there are atoms? That's something called a radial distribution function. How many people got that? How many? I just want to know. None of them. Okay. Okay. Let me explain and some other way. So you see there are different sizes of materials here. My laptop is this much size. This mic is this much size. This chair is this much size. So if you take a distribution of different sizes, right, you'll get something called histogram, right? That makes sense? Yeah. Similarly, in materials, there are different bond lengths, like silicon-silicon, silicon-oxygen, aluminum-oxygen. So these all, you can also make a histogram of that. That plot is called radial distribution function. OK, how many people got it now? Yeah, OK. I talk about bond length. Similarly, if there's an atom here, and I wish I had the other hand, atom here. So this is an angle, right? That you can also bin in a material. That's called bond angle distribution. And if you have one more atom there, it's called 4 atom, called dihedral angle distribution. So this is a sort of descriptor of a material, how we describe. This is called structural descriptors. Let me talk about chemical descriptors now. For example, you have aluminum and oxygen in your material. If you take the average electronegativity, okay, how many people know here electronegativity? That's good enough. So, or let me take a simple example, atomic mass. You take an average atomic mass of all the atomic species in your material. That's one number, right? If you take an average, that is also one descriptor. Similarly, we have made 1,557 such descriptors. All possible things you can think of in chemistry, like electronegativity, heat of vaporization, heat of formation, band gap of material, refractory index, something like that. We have 1,557 arrays. So if you give me a material like silicon oxide, I will convert this JARVIS-ML will convert into 1,557 descriptor. This is really an array. So you have an X array, and your Y array is like band gap, heat of formation, which you compute from actual density functional theory, like quantum mechanics, based on quantum mechanics. So you use your computers to generate the band gap and stuff and formation energy, and these are X and these are Y. Not just one material, but 20,000 of materials. So you have really 1,557 by like 25,000 array as X, and like 20,000 band gap as Y. And you find the relation using algorithm, like linear regression, logistic regression. So, so this is really what is actually happening. So you see here, it doesn't have to be quantum mechanics or classic mechanics. It's really finding trend in this. And I'll show you in a few minutes, it really works, surprisingly. And you can find the code for this at the GitHub page, US-NIST Jarvis. And this is our first plot. So we are just started working on visualizing this huge high-dimensional data. So we have 25,000 materials and 1,557 descriptors. So many dimensions, and we plot it into 2 dimensions here. So it's really a lot of crunching of information. So nice thing we found is there are different systems in materials. For example, if a material has same X, Y, Z, we call it cubic material. If it's a little elongated along Z, it's like tetragonal system. So there are different crystal systems, we call it. So surprisingly, the t-SNE plot was able to classify or make a cluster of these crystal systems just using the descriptor data. This is quite fascinating to me. And we are trying to find some other method to find such clusters. OK, so the idea is you are not clustered in on one cluster. I mean, if you are just doing machine learning on a cluster data, you're really interpolating. You're not learning anything. So we want to make sure that our data is really widespread. And then I show the different target values. So I talk about the formation energy. Remember the couple example thing? And then the band gap. And similarly, we have something called bulk modulus, shear modulus, sort of. Once I push something, it's going to how stiff they are. That's called bulk modulus. If you just strain it like in a particular angle, that's called shear modulus. So that's also computed using density functional theory or quantum mechanics. So these are, and there's something called exfoliation energy. So all the flexible electronics application is coming. Right now, you see the Samsung fascinating iPad and stuff, which are like bending. That's come from exfoliation energy calculation. I mean, and there are different other data, which like refractive index and stuff. This is an important point. This slide is actually made by DARPA, so government agency. So because as scientists, we really want to see the explainability of a machine learning model. If you do a black box thing, it's not going to work, at least for materials community. So we wanted to find out what are the algorithms which really explain a model. So we found the decision tree, for example, is one of the most highly explainable algorithm, which we want to use. And then I'll talk about something called gradient boosting decision tree. So it sounds quite complicated, but it's not that. Let me simplify this. Like decision tree. I think decision is the thing we really face in our daily life every day. For example, last night, I was watching a show on Netflix. I was thinking, should I complete the show or not, or go to sleep? These are decisions. Why? Because I have to wake up in the morning. So watching a Netflix show and waking up in the morning, these are your X and Y. And you take a 1 month data, and you can do machine learning on that. This is an example. So similarly, this decision making have different routes. Like, for example, random forest, and there are different algorithms which come into decision. But really, the idea is that. So a bunch of input and output data, and you find what is the best way to go from X to Y. And really, and you minimize your loss function. And if you want to read the details, it's really explained in this book, Elements of Statistical Learning by Hesty. So I use this model for something called classification of materials, such as whether a material is metallic or non-metallic, like has a band gap or not, and whether a material is magnetic or non-magnetic. So using the 1,557 descriptors for 25,000 materials, we found that we really get 96% accurate classification model for metal and magnetic material. So if you give me a material, silicon, my machine learning model will predict whether it's magnetic or not. I think that's cool, without using any physics. And we also, in addition to the classification, we fit a lot of regression models. So you have two classification and 12 regression models. I'm showing here only 2 of them. So we have to plot the learning curve. So you have to make sure that your data has your machine learning model has a lot of scope of learning as you increase the data, which is the figure number A. And then you have to split the 90 and 10% training and testing set. And what you see in the figure B is really the prediction on the test set. So that means you see a quite linear line. So we didn't train the model on formation energy, but it's predicting really well just using data analytics. And we do 5-fold cross-evaluation, doing this 5 times basically. And these are the different results of machine learning compared to actual density functional theory. So if you have a density functional theory of quantum mechanics data for a band gap, for example, which you calculate and compare to experiment, the mean absolute error is around 1 electron volt. But if you use, for example, machine learning is around 0.3 electron volt, so it's not too bad. So what we are saying is, again, we are not replacing the conventional science here, but we are using as a tool for conventional science as machine learning. And this is the important part we call feature importance. So we talked about radial distribution function, the bond stuff, and the angular distribution function, charge, chemical descriptors. So we wanted to find which are the most important features. So we found, which is, I think, obvious, the chemical features, the electronegativity and atomic mass, atomic radii, those were really important in training the models we just explained to you. And then it was the bond distance, and then it was bond angle, and lastly it was the charge descriptors.
Can I ask you a question?
Yes.
I'm assuming you don't use biochemical materials, but it's all physical materials.
Like inorganic materials right now. Yeah. But yeah.
Is there such a concept as isomorphs in the inorganic world?
It is.
Chemically identical, but structurally it can twist or have Z-forms.
Yep. Good question. So what is, yeah.
Well, you have to have the structural
Yes.
database to differentiate.
So this radial distribution function, angular distribution function, that is what distinguishes separate prototypes or isomorphic materials.
So your machine learning algorithm is using lots of different orthogonal properties from different databases to classify, to use the decision tree to drill down and classify to specific.
This is exactly it is. Yeah.
You explained it well.
Thank you. Okay, so to see, as you mentioned, the structural descriptors, the bond distance stuff, if you see on the right-hand side, the chemical features and then radial distribution function and angular distribution function. What we are showing on the right-hand side plot is as we add more and more physics-based descriptors, we improve the model or we decrease the mean absolute error. So what it is finding, and this is a key very important thing to note, the structural descriptors like bond angle and bond distance are really, really important for your machine learning model for materials. Let me talk about genetic algorithm. So it's really based on evolution of human beings or animal or any being, like living being. So you have on the left-hand side the brown and the right-hand side the red. So you can consider as parents, and on the down you see the offspring. So these are really combination of how to combine them in different way, right? So the idea is, out of these two children, which one gonna survive? And how do you know that from materials? So for living beings, it's quite easy, because you can, they generally have, in the old days, they used to have fight, and whoever wins, like, you know, that is survival. For here, it's really the energies, the energy of a system. If it's low energy, we call it stable. If it's high energy, we call it unstable. It's gonna die, basically. So that is how we implement genetic algorithm from materials. How many people got it here for genetic algorithm? Okay, let me explain why one more time. So there are different ways you can permute or combine atoms in a material, and that will lead to different combinations. So if you have like thousands of combinations possible of putting red and gray dots here, right, together. But which one has lowest energy, that is the only thing that's gonna survive. That will be our next future offspring or children structure. So, and to calculate whether which one is feasible, we calculate energies generally using classical mechanics or quantum mechanics. But where I propose is we can use machine learning for that. And I'm gonna show in a few minutes that we use machine learning to predict formation energy and see which is the most stable, and then we keep drawing it, not just one generation. We keep generating offstring structure, and what is the most stable structure. That will be the structure you'll be seeing in your actual experiments, not on computers. That will be the actual materials you'll be seeing in your experiment. So I did is molybdenum and sulfur. So this is one of the material which makes your flexible electronics fancy looking iPad or whatever. So molybdenum disulfide is a very fancy material inside of flexible electronics. So we took molybdenum, sulfur, and all the prototypes, like structural prototypes, how they can sit down, and let them mate with each other, sort of, in a computational way. If you want to see, there's a link in my in the slide. You can see how do we do that, actually, in computers. So you let it mate with each other and find what is the lowest stable structure and let it evolve. And with, for MO and S, we made 5,000 children structures. And guess what? Only like 8 or 9 survives. You see the blue dots? These are the survival children, basically. And others, the red dots, die away, basically. So we found, interestingly, that MOS2, which is known to be a stable structure, is actually a stable structure even in machine learning. I mean, I just don't know how to explain how big achievement it is, but it really sort of bridges the gap between the machine learning and the data science community. Not just MOS2, we tried on tungsten sulfide, and what we are proposing here, we can really do all the combination of periodic table elements and let it evolve. And we can see what's the most stable material for a particular composition. And on the right-hand side, I'm showing, for example, what the crystal structure of a survived structure looks like on the right-hand side. This is copper and MOS2. So this is sort of the validation process that we talked in my first slide. You can do a lot of black box machine learning, but unless you validate or do a metrology or set standards for how do you validate a model, it's just a data. I mean, it's good for exercise, but materials community is not going to accept it unless you do some kind of physics-based, constraint-based testing or validation. So this is one validation which we invented, and we wrote a paper on that and just submitted that. We use this machine learning model to find flexible electronics materials. We know, for example, MOS2 is one of the flexible electronic material. So we found around 5,000 2D materials, something called two-dimensional materials, which are possible candidate for that flexible electronics, which I think, in my opinion, can revolutionize the flexible electronics industry. So you can find what is the most stable, most stiff, have some, if you want magnetic material or not, if you want semiconductor material or not, then out of all your apps, the engineer can go and choose one particular material for testing and experiment, instead of like Edison way of doing combining different materials in lab and then do it. So it's like 1,000-fold acceleration in discovery, or maybe more than that. So this is a demo where I trained the model using Light GBM software, so from Microsoft. It's same as scikit-learn. And I pickled the parameter and made a Flask app, so you can predict properties on fly. So let me show you how it works. Not this one, this one. Showing here, OK. So this is just an app. So here I'm showing how a materials will look like in a crystallographic orientation. So I'm talking about molybdenum and sulfur. Oops, I did not. OK, molybdenum and sulfur. There are 2 molybdenum and 4 sulfur atoms, and I'm giving the molybdenum and sulfur atomic positions, where exactly they are in space. And based on that, I'm going to predict its properties. I click send. Wait for a few seconds. And here they are. The properties of this material, the band gap, formation energy, modulus, it's not using any physics or anything. It's predicting on fly. You can literally put whatever material you want, and it will predict the properties in a reasonable way. So I think this is acceleration in discovery. OK, let me go back here. OK. Oh, OK. So I talked a lot how this actually works. If you guys are interested, so you can go to our GitHub page, and you can download all the descriptors, the data, and I'm giving a short example here on my GitHub page. So this jarvis.sklearn, you can get it on the web, and you take something called postcard. The thing I showed you here, I call it a postcard, the position file, basically. And then once you give it the postcard file, it will give you the descriptor, like 1557 descriptor in one line. I mean, of course, there's a lot of back subroutines, but this is how it works. Once you get that, then not just one material, you can take the whole 25,000 material database and convert into a descriptor. And then I'm showing here a simple example. Out of 25,000, you take 5 materials, train their formation in energy, and subject to scikit-learn's gradient boosting decision regressor. I'm just saying for 5 materials. You can literally do for all 25,000 materials. And then this is my test set, like one material. And it will predict the formation energy using machine learning. So a lot of my colleagues are working to expand to different algorithm structure because I personally am not an algorithm developer. So I'm giving all the data to them, and they can collaborate on that, how to use different algorithms in machine learning. Okay, so we are really not just, as one of the people in the audience said, are we focused on polymers and molecules? So right now we train only on inorganic materials, but we are extending ourselves for molecules, proteins, for drug discovery, and medical diagnosis. And we have found at least 5 million materials like that. And we are going to visualize and predict properties using machine learning. We are doing active learning. It's another fascinating topic in which you train machine learning model and really combine it with experiment. It's something like speech recognition. The speech recognition is always learning from your words, right? Similarly, what you do is learn from the quantum mechanics data and subject to the experiment. And when the experiment goes on, it keeps on updating its parameter or keep learning as the experiments go on. So in using that, what happens is instead of sampling all the materials, you can really focus on what next material to go on. It will really save a lot of time and experimental endeavor. We are doing transfer learning. So we have different databases. So learn from one model, and instead of, for the other model, instead of starting from scratch, you can transfer the model parameters and learn continuously. We are also doing something called multi-output regression. So what I presented here was single output data, such as formation energy of a material, band of a material. But why not the whole material database in one array? So instead of predicting one output data, it will predict a continuous data. So that's why we call multi-output regression. So what I'm going to emphasize here is really a golden time for bridging the gap between the AI and materials community. It's really a hot topic for last 2, 3, or 5 years. And if you get it right now, you'll get expertise in this. And we are giving all the data, the software, to public domain. And you can, the web app we have developed using Flask, so you can hack around that too and make your own app or something. You can find the slide and my other slides at this SlideShare website. And this is our website for Jarvis, jarvis.nist.gov. So if you go to the jarvis.nist.gov, you'll find the information about a workshop called Artificial Intelligence for Material Science, which we are organizing in August. It's completely free. If you are interested, feel free to join. You have to sign up for some registration link because you need to have some security check and stuff. But that should be trivial. So you go to jarvis.nist.gov and go to the workshop button, and then you can register for the workshop that we are organizing. I think that should be it. I'm quite on time. Thank you.